All right, so now we're looking at doing the second simulation in 7.2. So last time we had a group of 8 people, and 25% of them were cat people. Now what we're going to do is we're going to look at, instead of having a population of 8, we're going to look at having a population of 1,000, and 25% are going to be cat people. So here's the deal. When we only had a population of size 8, what you'll remember is that we already had 70 ways of pulling a group of 4. Okay, if we have a population of 1,000 and we're pulling a sample of 10, there are tons and tons and tons of ways to do that. So we're not going to write out all the different ways. Okay, so what we're going to do instead is we're going to have a computer program randomly take samples of 10 people. It's going to calculate the sample proportion. Okay, that means the number of people that are cat people in our sample. And we are going to repeat this 10,000 times. Okay? So what that is going to give us is that's going to give us the sample distribution below. So really quick, let me just point out how you would interpret this. What this means is out of the 10,000 samples that we looked at, about 500 had 0% cat people. Okay, so that's how you would interpret this. Now, if we look at this, here's some of the information that we get. Even though this doesn't look super normal, it's relatively normal. Okay? What we can see is that the mean, or the center of the graph, is still 25%, and the standard deviation, remember this is also called the standard error, we'll call that SE, is about 13.56%. So if we're looking at this and we want to ask questions like, hey, what is the bias? Well, again, since we didn't go to just a cat cafe or a dog park to get these samples, we did it randomly, what that means is that we're going to have no bias. And the way you can prove that is that the average of our sample distribution equals 25%, which is also equal to our population, which means our bias is 0. The precision is we expect to be off in our sample, on average, about 13.56%. Now, a way that you guys can think of this, if you wanted to write like a little summary or interpretation, is that our samples will be 25% cat people, give or take about 13.56%. Okay, so our precision still isn't great. I mean, if you have 25% cat people and you expect most of your samples to be off by 13%, you're not doing super great. Okay, but in general, as long as our population is large compared to the sample size, the precision actually has nothing to do with the size of the sample. It only has to do with the size of your sample. What that means is that a sample in a group of 10, what that means is that the sample size of 10 in a population is just as precise in a population of 1,000 as it is in a population of 1,000,000. Now what you might be wondering is, why is that true? And here's why that's true. If I have a little bowl of soup, and then I have a big bowl of soup, and they both contain the same soup, I'm going to get the same sample or the same bite, okay, if I use the same size spoon, okay? The only thing I have to make sure is that it's going to be mixed. So both of these are going to give me the same bite of soup. which in this analogy is a sample. They're both going to tell me something about the same population. Now, in the last simulation, what we do is we're still looking at a population of 1,000 people with 25% cat people. However, instead of doing a sample of size 10, we're going to do a sample size 100. So again, we do this a lot, and what we see is that most of our samples are still going to be 25%. What that means is that our bias, or how much most of our samples are off from the true population, is still 0. Now the cool thing is that our standard deviation, aka our standard error, has dropped down significantly. So instead of our samples being off by probably 13%, on average now they're going to be off by only 4%, which means that our sample's more precise. So when it came to the 3 sample sizes, what did we learn about the estimate p hat? So we learned that p hat does not always equal p, but most p hats will be close. So it doesn't always equal p, it definitely can, but if it doesn't, most of them will be close. In our precision, this is also something important to remember for your guys' final exam. What happens to the precision as our sample size gets larger, as n, our sample size, increases, our precision increases, which means our standard error goes down. So the amount that we could be wrong goes down. And what happens to the shape of our sampling distribution as our sample size increases? It gets more normal and narrow. It gets more narrow because our standard error decreases. Now, we can find the standard error, but we have to make sure that we have the following conditions met. So finding bias, that's one thing, but finding the standard error, here's what we have to do, is first we have to make sure that our sample is randomly collected. Okay, what that's going to do is that's going to reduce bias. That means that we can assume that our bias is equal to 0, or that most of our samples are going to reflect the population. Okay? Now, if we're sampling without replacement, that means if I'm running around getting a survey out, you can't take my survey twice, the population needs to be much larger than the sample size. And what a good rule of thumb is that our sample, okay, and our population, well, our population should be 10 times bigger than our sample. The reason for this is that even though we've been harping on having a really big sample, we want to have a big population because that means that we can repeat our surveys over and over and over and over and over. Okay? So, to calculate the standard error, we are going to use this formula here. Okay? Where p is the actual value of our parameter of interest, that's going to be a percentage, and n is the size of our sample. Okay, so remember, the standard error is the standard deviation of our sampling distribution, so the lower that is, the better the precision of our method. Okay, so let's do an example of this. Suppose that we have a population of 1,000 people, and 25% of them are cat people, and we take a random sample of 100 people. What value should we expect our sample proportion to be? Well, since we did this randomly, we expect our samples to be the same as our population, so we expect p hat to be 25%. Our standard error, so how far off are we going to be, is going to be the square root of p times 1 minus p divided by n. Now n is the size of our sample, not the size of population, which is 100. So if we round that to about 2 decimal places, here's what we're going to get. We are going to get 0.04, I'm going to round it to 4 decimal places, 0.0433. Now what we want to do is interpret these values. So here's what that means. a sample of 100 will most likely be 25% cat people, give or take 4.33%. All right, now, in real life, we don't know the value of the population proportion p, so what we're going to do instead is we're going to find the standard error estimate. So you're only going to do the standard error estimate if p is unknown. So if you're given an example where p is unknown, then you're going to estimate the standard error using this guy. Okay? So what that does is that usually we don't do a sample a million times, right? We don't repeat a scientific method a million times. But even after one time, we still want to know, hey, how far off are we from the actual population? And you can estimate that using this guy. So n is still the size of your sample. But don't forget p hat is the size of your, or is the percentage of your sample. So, for example, okay, let's say that we are interested in the proportion of art majors to the entire college population here at OC. So we find that out of a sample of 120, 37 are art majors. What we'd like to do is calculate and interpret the standard error. So the first thing is, notice that I didn't get the actual population, I just got a sample. So first I need to calculate p hat. So I took a sample of 120 and I found that 37 people were art majors. So I'm just going to round that to 4 decimal places. So that would be 0.3083. And I'm going to use that to find the standard error estimate since I don't have the actual population p. So that's going to be 0.3083 times 1 minus 0.3083 divided by, remember, the size of my sample, which was 120. I'm also going to round that to 4 decimal places as well. So that would give me 0.0421. So here's what that means. So usually we would have p and we would say something about p hat. So we have p hat now, we want to say something about p. So this means that we expect the population, which is p, to be 30.83% art majors. Now we know that our sample is not going to mirror the population exactly, so we want to tell people, hey, it's probably around 30%, give or take. So give or take 4.21%. Okay, then we would feel pretty good about that. All right, great. So now we are going to be moving on to 7.3 and then 7.4, which is going to be talking about how you can use these to give really good estimates.